All right, greetings everyone. So today we're going to be talking about stacks, queues, and such. Talk a little bit about linked lists, just sort of in vague terms, um, and hash sets. Because we have been looking a lot at the Java list class, and we saw that the list class had these words. And in class we also looked at sort of the efficiency and how some of them were faster than others. But let's actually let's look at why. Um, so fortunately, a lot of these structures are going to be very similar to how we use them in English. Like we've heard of the word stack, right? Stack of paper on my desk or something like that. We've heard queue, like you're in a queue to get your bread at the bakery. Um, that these are words that we use for everyday discussion. But this linked list and this hash set, those are maybe a little less so. Um, that the word hash, especially here in Santa Cruz, has a very different meaning than the use that we use in programming. Okay, so hopefully everything's good in Jeff land. All right, Jeff server's up. And his website's up. Okay. Hopefully you've done assignment 7, and then let me know if you have any requests. Okay, so a stack. So literally the same way that we think of a stack, and when I say literally, I mean exactly what I'm saying. That I am saying what I mean to express. The definition of literally, not the teenager version. So a stack is literally a stack of things. It, like if you were to place, if you were to have a stack of plates, you can always think of it like the restaurants that have that giant spring at the bottom of the plate stack, that it only reveals the top one. That as you put more plates into it, they sink into the cabinet and they're down there. That you can only interact with the thing on the top. That you can either put a ton of things on the top, right? You can add a plate to the top, or you can take one onto the top. And so a stack is called the last in is the first out, or LIFO, right? The first one, the last one that you put on top of the stack is also going to be the first one that you get when you go to grab a plate. So the first one that you put in will be the last one that you get out, right? So you can think of it as the flip side. So you don't really want to grab in a stack of plates when it's empty and you're grabbing that last plate when it's really busy. That's pretty nasty. Like you might want to wipe that plate down or something, because it's been down there for a while. So that's a data concept that we should think about, right? Just like a stack of plates, that if we add something into it, that the top of the stack will then change to whatever element that we just added in. And then when we go to remove something from it, that we're interacting again with the top. So that's a stack. It's exactly how we use it in English, and it's a fairly useful data structure. And you should be able to implement a stack. If I asked you to write a class that uses stacks, if you think about it, this bottom of the stack could be the front of an array, right? The beautiful thing about encapsulation with classes is that you could write a stack class and all you need to implement it is an array and some methods. And essentially you would be hiding from whoever's using your class those methods. So you might have a method that's the size, and you might have and then an enqueue, or yeah, sorry, sorry, I'm skipping ahead. You have a push method that adds stuff. So the push method will take an argument of the type of the stack that will add it to the stack, and then your pop will remove it. And there's sort of a mix of how people do pop. I always think of pop as it both removes and returns the element that's on the top of the stack. So that when you call dot pop, the stack dot pop, it's going to delete that thing off on the stack and it's going to return it back to you. So you're going to get E for pop. There are some people that use pop where they only remove it. They don't return the value. Maybe they return the status of pop. Different people implement it differently, and you'll see in a specification if you have to implement a stack what people want. But I prefer pop to remove the element and return it at the same time, because otherwise you would have to read what you would have to say, like stack.top and then stack.pop, which is just 2 extra calls. Okay, so that's a stack. Pretty straightforward. Let's and yeah, so to push to pop, and it's a LIFO. So you might hear people say implement a LIFO structure. All they're asking is implement a stack. Sometimes people will use this vocabulary either to feel intelligent or because they feel that this is more descriptive than a stack. I don't know. But just be aware that people will say LIFO instead of stack, which aggravates me, but that's just how the cookie crumbles. So yeah, stacks, beautiful things, just we can think of it just as English. All right, and then a queue. It's just like a line without fast pass, right? That there's no, you're not skipping in the queue in this case based on anything. You're in a line. Yeah, just like at the beginning when you took a number that, unless if people left, that would be the number that you would have to wait that many times for, whatever was displayed. And so this we use enqueue and dequeue. And so this is a FIFO, or first in, first out. So a line, right? The first person who gets in line is the first person that gets to do whatever it is. If that's getting food, if that's getting into the movies, if that's getting into your concert, whatever it is. If you're the first in line, there's nobody with fast pass or VIP things, none of that. Then you will be the first person to get out of the line and into the venue. And so to get in line, you in queue, and to get out of the line, like you're at the front, and you're being served, then you dequeue. So yeah, NQ is to get in line, DQ is to get out of the line, or to be to finally got to the front and then be consumed from the front. So yeah, a FIFO, first in, first out, is a queue, just like a line. And then you've seen like priority queues. That's essentially where there is this sort of fast pass, that some part of the value of that object is going to change the ordering of it. So yeah, priority, right? We can think of as like the fast pass, the way to skip ahead based on some attribute that you might have. Okie dokie. Now let's get into the crazy parts. Linked lists. So I love the deck of card example for linked lists, and I honestly don't see it enough. I know of one assignment that is used that linked lists make your life much easier, that we do at Cabrillo and Steve Hodges' class. But linked lists are not emphasized enough. They are incredibly powerful structures um, because they allow us to do things like this, that we see this card shuffle right here. This is a triple cut, right? What's happening is that the top part, essentially, this chunk gets put down at the bottom. And the beautiful thing about a linked list is that you can interact with chunks of the linked list or insert a chunk. Like if I wanted to add this pile, let me turn on the laser. There we go. If I want to insert this pile into the middle of this, that's a very, very easy operation. Literally coding wise, adding an extra deck of cards into the center part is exactly the same amount of code that it would take to add a single card, assuming that this was already constructed in a linked list. To add one linked list to another linked list is the same amount of code as adding one link node, a single thing, like a single card, into this pile. And so it's the same thing like when we're interacting with a deck of cards, that if there was another deck of cards sitting on this table and he wanted to add it, you would just simply pick it up and put it on top of the deck of cards. That you don't need to rifle through, you don't need to have a for loop or anything that goes through the whole deck of cards, because a linked list is only dealing with the interactions between the edges. So essentially, if we say, hey, 7, what's your next card? And it says, oh, it's this ace. And then you say, ace, what's your previous card? That's called a doubly linked list, where they go both ways. But it might be for a singular linked list, and you don't need to know any of this. This is just extra information to help you appreciate what's going on. So essentially, in a single linked list, let's just start there, I guess. You only keep track of the direction one way, of the relationship one way. So we say, so we have a front, which points to the 2, and we have a back that points to the 6. And then each of these cards knows which is the next card. So if we ask the 2 whether it's next card, it's something extra in this pile. If we say, hey, 7, what's your next card? We say ace. If we say this ace here, what's your next card? We see the 5. And then if we ask the 6 what its next card is, we do something called null termination, which we essentially point the 6 is next to null. And that's how we know that we're at the back. But we can also point an extra thing to the 6 that says this is the back. And so if we needed to print out all of the deck of cards, we could go through it until we either hit null or until we hit back, whatever's pointing to this 6. So we can ask, hey, is the reference that we have the same as whatever card that we're looking at now? Okay, so yeah, so essentially, to do this triple cut right here, I looked at this for a while. It goes really fast. I wish I could slow it down a little bit. But essentially, the top chunk here, which we're going to say is this 2 to 7. First the first bottom piece, which happens to be this 5 to 6, that gets put on top of this. So this pile here goes on top of this pile here. And then, if you notice, then he does that one right there. So first there's that, so that's the 5 and 6, and then there's the second part, which is the 2 to 7. And so what happens? Oh, sorry, which is the aces. So that little pile that he does at the end is the aces. So right there, that's the aces. So the aces there then get moved to the front. So notice that in these 3 chunks, that we've essentially reversed, or that we've changed the ordering of them with this triple cut. Right, that what was in the middle is now in the front, and what is in the back is now in the middle, and what's in the front is now in the back. We've changed that. This triple cut here has very much changed the ordering of the deck of cards. And what's great is that we don't need to care about any, like the ace of hearts or the ace of diamonds. We don't, or any of these dots, any of these triple dots. We don't care about those because in a linked list, whenever we're writing code, because we only care about when we're shuffling them. So all we had to do this whole operation was front got changed from the first, for that first cut in this triple cut, front went from pointing to 2. So it's literally just front points to whatever this is, this class object. So front points to this, and then when we do the first cut, we change front to point to the 5. So front, the object, whatever object we're pointing to, points to 5 in the first cut. And then the next thing that we change is we change the 6. We say this 6, instead of pointing to null, is now pointing to 2. And that's it. We literally change 2 things. We say front points to the 5, and we say 6 points to the 2. So we've changed two things to essentially do the first cut. And it doesn't matter what's these dots or these dots. So imagine if you had to do that in an array, right? In an array, you would have to make a new array and then copy everything over in a particular order, which can not be too easy, especially if this triple cut is changing in size or whatnot, or you're maybe picking up a new deck of cards and adding it in. It's much more difficult to do. Okay, let's do the second cut, or we'll do the last of the triple cut, or the second cut. So we've changed front to point to 5. I should probably stick in intermediate. Definitely don't have enough room here. Okay. So the first cut, I don't know, this is just going to look really busy. So the first cut is sticking the 5 and 6 in the front. Okay. Okay. I don't know. That doesn't improve anything. Maybe I should just erase that border. Make our lives a little easier. Okay. I don't know. Sorry, this is not the best. Yeah, I should probably add that border back. So this was the first step. So now the 5. So the first cut, this 5 is now in front, and 6 is next, is pointing to 2 when it previously pointed to null. So now, let's see. Okay, yeah. So now there's ace in the back. So now let's do the second cut, or the triple cut. Now we're going to do that extra little slice. So that's the first cut, then that's the second cut. So right there. So that's us moving these aces all the way up to the front. And so all we change is this ace here points to null. We change this guy to now point to the 5. And this ace of spades here, we're going to say front goes to this guy. And then Now the 7 is going to point to null. So we say 7's next is null. And there we are. We're done. So one of the things that I like to do, though, is that instead of pointing to null, you actually link the two. And I call it a circularly linked list. So instead, I would just leave this relationship from this 7 to this ace of spades connected instead of pointing it to null. So that the ends point to the front. So essentially, if I was asked to count through a deck of cards and then place each, as I count through each of them, I was to place them at the bottom of the deck, that I could count as many cards deep into the deck as I want, because when I say, hey, 6, what's your next one? I go back to this 2. And then I just keep going, keep going, keep going. And when I hit the end, I actually don't even know that I'm at the end, that I just keep counting. So that's just a useful thing with linked lists. I like to physically think of them as a deck of cards, how each card by itself has a relationship with the cards around it. And that if I was to, shuffle a deck, that all I'm doing is that I'm taking, if I'm shuffling a deck, that hopefully in between these spots, I'm going to be inserting another a card in between all of these. So linked lists are very, very good at doing operations where you're keeping chunks of data either in relation to itself or like a shuffle like this, where this chunk of data here sort of stays together in this one context, and that it moves relative to this other chunk of data, and that the connection that you have to do, this first connection, we literally only had to change one. This ace points to null. This 6 is going to point to 2, and then that's it. Oh, and then front changes to 5. So we changed 3 things for an entire deck of cards for doing a cut. Versus if we were to do this with a for loop and an array, you would have to touch each individual card and you would have to create a new array. You have to copy them all over. So efficiency-wise, a linked list is very, very good at doing these kinds of operations, and the code is very, very simplistic. Once you dive into it, I don't think we need to know about linked lists for this semester, but for next semester and the following semester, if you continue coding, you'll definitely be working with linked lists, but you'll have a much more formal lecture around that. But just so you can get an appreciation and understanding why linked lists, when you were doing tests in class, were faster at some things but slower than other things. Right? Because if for example I said, hey, print out everything in the linked list, it's a little bit more effort than going through an array. Not much, but just a tad more, and that little extra, depending on what if you're for example storing things as a queue or a stack as a linked list, that works perfectly fine. Linked lists can do that. They're very versatile. The thing though is that instead of so for example, when we were looking at a queue, a linked list makes a lot of sense in a queue because we're not dealing with an array, right? Because one of the things that if you were to have a queue as an array, when you dequeue, now what do? Do you copy everything over to the next spot in the array so that whatever index of the array 0 is always the thing in the front. Well, that means that every time we you have to, as this gets longer and longer, and we have to shift everyone over one, that's terribly inefficient. So a linked list makes a lot of sense for implementing a queue. We could do this as an array. It would just be terribly inefficient. But like a stack, for example, where we're only dealing with the top or sort of the back of the array, that a stack makes a lot more sense to be an array than a linked list. But you could implement a stack with a linked list. There's nothing stopping you. Okie dokie. So hash sets. So we might recall that a hash is a trapdoor. That it's this one-way, that it's a one-way function. And you might have heard that in math. If, for example, I was to give you 4 numbers and I was to add them together and then tell you that the number was 10, that the sum of those 4 numbers is 10, you couldn't know, right? Because these could all be 0 except for one of them, and it could be 10, right? There's tons and tons of possibilities for numbers that could all add up to be 10. They could be negative. They could be, I mean, there's all kinds of different numbers. So this isn't one of those silly, Facebook games of, how many bananas and witches and pizzas, and adding them together to get some number. This is hashing. And addition's fairly broken because there is a finite, there's a finite number that can much easier be worked backwards. But a modern hash function uses lots of different kinds of tricks to make it much more difficult to make an educated guess. Right? For addition, we could immediately look at that 10 and come up with some possible solutions. And so there's a trade-off of it either having so many options that it could be, which is not particularly good, because then that means you have what's called a collision, right? Say that my computer, for example, when you type in your password, it's not actually checking your password. What it does is it does a hash. It does an operation with whatever I just typed in, and then it compares the hashes. And so if we had this addition thing, if the password was 1, 2, 3, 4, and we got 10, if instead somebody went up to the machine and typed in 0, 0, 0, 10, enter, they could log in because the hashes match. We don't want that. Collisions and hashes are bad, especially when you're using them for passwords or authentication. So we do ways we have ways of reducing the collisions, and I'll talk about that in a few seconds. But also we have algorithms that are much better than addition. Maybe each of the spots, you change their weighting. So the first number that we get, we keep it the same. The second number, we maybe multiply it by 10. So instead this is 20. And then here we multiply this by 100. And then here we multiply this by 1,000. So now we have 4,321. They don't see the hash. Or maybe they see the hash, depending on how you're using this hash. But in that context, in this algorithm of addition, if they know the algorithm, they can immediately look at that and know what numbers and what order were given. But that there's no chance for a collision. The issue, though, is that number, 4,321, is a very, very big number. And the bigger the hash number is, the bigger sort of the more space that you have to have. I'm trying to. Okay, so think of a hash set as an array, and the hash of something is the index of the array. So the spot in the array where something exists. Sorry about all the noise in the background. So if I said, hey, the space that exists in the array is size 100, then that means that the hash has to give me something between 0 and 99 always. That maybe there's a modulus of oh, let me field. All right. Sorry about that. I just got a phone call from my grandmother. Everything's okay. Her computer is just being a little grumpy. So yeah, hashes are trapdoors. Hopefully that they work one way, but that the output of a hash sort of needs to be limited, because if we think about it, that's the size of the array that it's going to be placing it in, and that whatever the data that it's hashing is something that we set at a class level, that each object, when you say object.hashcode, so all objects in Java have this hashcode method, and we can overload it, we can rewrite it, we can say what things about an object are important for us to hash. So there might be some data that when you insert that object, that instance of an object, into this hash set, that you want them to, even though they might be not identical, maybe there's a timestamp or something that's in it that makes them different, but you want them to collide. You want them to essentially, that only one of them gets preserved. So say you go in and you go to create a new account, but that your username is the same and your password is the same, it's going to tell you, hey, that's already in the hash set, even though that you are doing it at a different time, and maybe there's like a last login thing in your user class, for example. That part of the object is different. The last login, that data is different, but we don't care about that. What we care about is their username and maybe their email. That those are the things that we look at when we're deciding whether or not it's a duplicate thing. But there's all this extra data that doesn't matter. And I realize that you don't see any of my hand gestures. So this hash code essentially is determining how an object is being hashed, and we can change that. So yeah, that's the big takeaway from hash sets, is that they is that it's going to take the object, it's going to hash it with this hash code method, and based on that, it's going to determine where in the array that it lives. And the word set, if we recall from Jeff's lecture or from math, a set is essentially, we can think of it as a list of things that there's no duplicates and that their order doesn't matter. In a set, the order, if I was to pick up some object that I wouldn't know where it necessarily belonged, or if I picked up all of the objects inside of this hash set, I don't know the order that they exist in. without me having to go and then hash them. And the hash then indicates where they live. But the nice thing is that maybe you have something that's in this nice sequential thing, like this a 1, a 2, a 3, and a 4. But when you hash the number 1 or hash the number 2, that where they live in the array is radically different. And that's also the beauty of a hash set, because it helps sort of evenly distribute, well, hopefully sort of evenly distribute all of your objects in whatever data structure that you're using. So imagine your hard drive. If you have a solid state hard drive, like the idea of where leveling, where everything's sort of spread out, that can be useful, because then you're not wailing on the same spot in your on your hard drive, that you've sort of spread out the workload amongst different parts of it. And so a hash set is doing that same kind of thing, is that it's spreading out, that it's a way of spreading out your data all over the place. But also it allows us to be able to store more data than it allows us to be able to store more data than the array size that we have. And let me sort of clarify that. If I had an array and I was fixed based on the indexes, I could only store the numbers. Say that it's a Boolean array, for example, that I can only store true or false, and I'm trying to keep track of what I'm storing. I could only store, if it's size 10, that I could only store the numbers 0 through 9. But the nice thing about a hash set is that it's that the hash is going to be limited to outputting 0 through 9, but that I could insert the number 55 into it, because the hash is going to then be limited to that range of the array. So I can store more kinds of things in a hash set than just a traditional array, because of that attribute. Okay, so yeah, that's pretty much time for us. So we talked about stacks and queues, we talked about linked lists, we talked about hash sets, and really, hopefully you've opened your mind a little bit to how we order things, not only in programming and coding, but also physically. When we're looking at a pile of books and how they're ordered from top to bottom or side to side, or from page to page, or a deck of cards, that it's really important to look at sort of how we are naturally ordering things based on convenience for ourselves, and think about how you could implement that programmatically. That's always a good mental exercise. Okay, that's what I got for you today. Kapla.